Shafiq Ulwasir, Guy Rothblum, and he will talk about computing in the presence of leakage.
Thanks. So the talk today will have to do with computation, and in particular, what I'll be concerned with are sensitive computations. So sensitive computations, a couple of examples you could think of. The first, which I guess is very much in the theme of what we've heard about today so far, are cryptographic computations, which typically have to do with computing on secrets. We want the secrets, say the secret key for an encryption algorithm, to remain hidden. That's sensitive information that we're computing on. That's one motivating example to keep in mind when we're talking about sensitive computations. But another example could be, or other examples could be completely non-cryptographic in nature. So any kind of computation or any kind of data that we're computing on that has something that we don't want to be publicly revealed, maybe a proprietary algorithm or a public algorithm that's running on sensitive medical data. Both of these are examples of computation where we wouldn't want the entire computation and its internals to be made public, revealed. So we're thinking about sensitive computations, and one reality in today's computing environment is that these kinds of sensitive computations are being performed remotely, and in particular, they're being performed in adversarial environments where we might be exposed to attacks. One reason this could be the case is because more and more computations are being run on small mobile devices, devices that are running just physically in an environment that isn't they're not running safely at home or safely in our offices, but they're out in the wild, and maybe an attacker has easy access to them. So the devices are more plentiful and small and all over the place, everywhere, and might be attacked. And also, not only are the devices getting smaller, but also many computations are getting bigger. So, in fact, so big that they're being performed remotely. So cloud computing, for example, in cloud computing, a lot of data is being stored remotely. It's on a remote server. Who knows who else is on the server and who else could access and attack a computation or data that's being done remotely. So we have sensitive computations in adversarial environments, and the concern is that the internals of the computation, what we wanted to keep secret, might leak out. So that's the concern for the talk today. And in fact, it isn't only a theoretical concern. Actually, such attacks have been launched, especially on cryptographic computations, and have broken cryptographic schemes that are provably secure without leakage, or perfectly secure when the attacker's access to them is only as a black box. So that'll be the concern for the talk today. What happens when there's leakage on the internals of a sensitive computation? What we really want is a way to perform our computations in a leakage-resilient manner. That's at a very high level. And staying at this very high level, you can identify two very different approaches that have been taken in recent literature. The first is taking the leakage, taking the kind of attack you want to protect against into account at design time, when designing the algorithm. So we think in advance about what leakage we might be exposed to, and we build a specific system with specific goals that's secure against the leakage attacks. For example, and there's been a lot of work on this in recent years, for example, leakage-resilient encryption. Encryption schemes that are resilient even when part of the secret key is exposed, or some information about the secret key is exposed to an attacker. So that's one approach. The second approach, which will be the focus of the talk today, is actually maybe working harder, but only working harder once. And somehow managing to construct what we call a leakage resilience compiler, an automatic way of taking general programs or even protocols and making just any old program resilient to a wide variety of leakage attacks. So instead of working with a specific goal in mind, building a general compiler that can be used again and again and again. And the goal is to make the program resilient to leakage so that even if an attacker gets some sort of leakage access to the execution, he or she won't learn anything more than the black box behavior of the program, anything more than input-output access to the program. So this is what we'll be after in the talk today. This is our holy grail. And of course, it's harder, or we're after a more general tool than just a specific scheme with specific goals like encryption. So it's a harder goal, but in fact we'll show that for some varieties of leakage attacks, we can achieve it. So a little bit more about this. The way I want to think about it is we have some computation, which I'll model as a circuit throughout the talk today. So we have some circuit, and the circuit has some secret information, okay, some secret Y. You can think about the circuit as a cryptographic, say, signing algorithm, and Y is the secret signing key, or you can think about it as some algorithm that's running an analysis of a medical database, and Y is the sensitive medical data that we're trying to protect. And what the computation does is an input gets fed in, a public input X, and out comes an output that depends both on the public input X and on the secret information Y that we're trying to protect. So that's the functionality that we have in mind, and what we'll seek is a general compiler that takes such a program and transforms it into a new program with the same input-output behavior. Okay? So for an input X, we'll get the same output as the original program, but the new program C prime should also be resilient to leakage attacks. So even if an attacker is given some sort of leakage access to the internals of the program isn't completely opaque, but some of the internals are exposed. Even given this leakage, an attacker learns nothing more than the input and the output. Okay. That'll be our goal, and in fact, what we'll want is to do this for programs that will be executed multiple times. Okay? So not just for a single execution, but repeatedly inputs are chosen, then there's a leakage attack on the computation, and the attacker learns nothing more than the input and the output. So we want a compiler for sort of continual execution of a program, and I'll just remark that I'll allow this transformed program to be stateful. Okay, I'm just saying that right off the bat. It's a stateful program. Every time it's fed an input, it produces an output, and it updates its state.
Just as the original one is stateful, right? So you start with
so the original one is stateful. This is going to be a dynamic state. So this one wasn't necessarily dynamic. Maybe the secret was just a static signing key, and here I'm allowing changes to the state. Okay. So that's our goal, but maybe if you're informed and quick thinking, you might tell me that this goal is impossible to achieve, and you would be right. So what do I mean by that? The holy grail that I described, if we look a little bit more into it, is a way of taking any program, C sub y, with the secret information y plugged into it, and outputting a compiled program, C prime. And what we would want is that for every execution of C prime on some input, the first input is x1, second input is x2, in general for an input xt, an adversary can choose whatever leakage function it wants, whatever efficiently computable leakage function it wants, and measure that leakage on the entire internal state of the computation. So on the entire internal state of the leakage resilient computation. That's our holy grail. Unfortunately, and this follows from the work of Barak et al. On the impossibility of obfuscation, even if we only allow one bit of leakage, just one bit of leakage on the internal state, very small leakage, if the attacker can choose any polynomial time computable function, then one can show that there exist functions for which any compiler will fail. The adversary will learn non-black box information, and in particular, leakage resilience compilers don't exist. So this holy grail, in its full generality, isn't achievable.
this is 1 bit global or 1 bit per execution?
Per execution. Even 1 bit global, I believe, would be enough. Even 1 bit global is impossible. So still, I told you that I want to tell you about good news, positive results, that we can achieve the Holy Grail in some sense. And in fact, what I'll talk about is new work, where we show how to compile any program into a functionally equivalent, any program C sub y into a functionally equivalent C prime, such that even under leakage attacks, an adversary doesn't learn anything more from the executions of C prime than it would from black box access to CY, to C sub y. Moreover, the result that I'll talk about is unconditional. So I won't make any cryptographic assumptions. In particular, the adversary will be allowed to run in exponential time. I won't use any secure hardware. I won't use any secure hardware, unlike some of the previous work, which I'll talk about. And one more thing that I want to emphasize is that this guarantee, the quality of the guarantee that says that the executions leak nothing more than black box access, basically say that you completely preserve the underlying security of the original computation C sub y. Okay, so if the original computation C sub y had any kind of security, say cryptographic security property under black box access, then the transform program will preserve the same cryptographic security property even when the adversary is given leakage. When the adversary is given leakage to its internals. So far so good. This sounds very nice, but I also told you that this was impossible to achieve. So you should be asking what gives. And what gives is this little star after the leakage, after the word leakage. We won't allow arbitrary polynomial time computable leakage on the internals of the computation, but rather we'll only allow local leakage. So leakage on local areas of the computation. And this follows along the lines of earlier work or an earlier suggestion by Micali and Raisin. The leakage will be allowed to work on local computations rather than on the entire global computation of the circuit. So let me tell you a little bit more about what I mean by local computations. The way I think about it, or the way we will think about it throughout the talk, is that the computation is divided into ordered subcomputations. So it's divided into an ordered sequence of steps, step 1, step 2, step 3, and the leakage operates separately on the data that's computed on in each of these steps. Okay? So the leakage operates on each step of the computation separately, although it's allowed to be adaptive. So the adversary is allowed to choose its leakage functions adaptively, but it'll operate separately on each step of the computation, on each subcomputation.
So does it mean that it doesn't depend on the history of the prior instructions?
So it depends on what the leakage has been from the prior instructions, but it can't access the prior instructions in their entirety. Okay. So one useful abstraction for thinking about this, or an equivalent model for thinking about this, is what we call a leaky CPU. Okay, so what we have is a CPU that runs atomic operations from some small set of atomic operations, and every time it operates as a CPU does. Every time it wants to run an instruction, it goes to memory, it brings in some information from memory, then it runs a computation on the information it brought in, and then it writes the output back to memory. And when I talk about a leaky CPU, what I mean is that whenever you fetch something into memory, whenever you fetch something from memory onto the CPU, there's leakage from that. When you compute, there's leakage from the computation, including any randomness you might use. And then there's leakage from whatever output you write back into main memory. But the leakage operates only on what's being computed on, only on what's being fetched into the CPU or written out of the CPU. It doesn't operate on the data that's in memory and isn't being touched.
Suppose there is a bound for leakage per cycle, per computation.
Right. So that's a leakage model, and in particular, what will also require is a bound on the leakage. Not everything is exposed, but some bounded amount of information. I'll say a little bit more. I'll give a little bit more details on the next slide. So this is the class of leakage attacks that we'll talk about. We call this only computation leakage. This goes back to Micali and Raisin's work on only computation leaks information, where this model originated. So those are the kinds of leakage attacks that we'll handle. Moreover, what the model that we'll work in is what we call an offline-online model. We'll allow an initialization step that's performed offline, where we process the circuit C and the secret Y, and we generate some initial state. And we assume that this is done just once at home or in the factory without any leakage. So the adversary doesn't get access to the single initialization phase. And in fact, one can show that this is inherent. If the adversary has leakage from the offline state, it can leak, for example, the first bit of Y. It's learning non-black box information. Okay, so in initialization, there will be no leakage. But then after that, we're going to repeatedly run executions of this circuit any polynomial number of times. And every execution, the adversary chooses the input. So the inputs are adversarially chosen. Then we compute the output, and we compute a new state. So there's a computation of the output, and we compute a new state through an update procedure. And the adversary observes the output, and whatever leakage function it chooses on the input, on the entire internals, and on all the randomness we use. So the computation is allowed to be randomized. And the adversary can choose any leakage function that it wants, as long as it's from this family of only computation leakage functions. So as long as it's operating locally on the computation rather than globally. So those will be the kinds of adversaries that we're concerned with. And now I'll tell you exactly sort of the parameters of what we can achieve. So we can transform any computation C sub y, and for chosen security parameter kappa, there's only polynomial blowup. So the transformed circuit will only be polynomially larger than the original. The subcomputations, the steps on which the leakage will operate, will be of polynomial size. Here the polynomial is k to the omega, where omega, we'll see later y, is the exponent for matrix multiplication. Okay, so somewhere between 2 and 3. It's been rapidly changing recently. So. And as Evgeny asked, we'll allow a bounded amount of leakage from each subcomputation. Okay, so the adversary can choose any k-bit function, any function with k bits of output, and receive that leakage on each subcomputation.
Okay. What about randomness? So if the computation is, let's say, deterministic,
Mm-hmm.
like the PRF, your transformation will also be deterministic, or you will use randomness even then?
No, we use randomness even then.
Well, not as the original transformation, but after the original leak-free component is done.
No,
the
we
rest-
use in every evaluation, we use randomness, and in fact, I think this is inherent. If you don't use, I think this is
All the
inherent.
updates are deterministic, so you can.
future computation.
There's a
I think you can do look-aheads. You can sort of, you can start in the first computation step, you can sort of ask, you can determine the first bit of the update, in the hundredth of the thousand. In terms of the security guarantee, I told you that the adversary will learn no more than black box access to the original function. And in fact, what we show, it's a simulation-based guarantee. So the entire view of the adversary, all the inputs and the outputs and all the leakage it sees can be simulated just by using black box access to the original functionality. And I want to emphasize here the adversary is not bounded in terms of its running times, and even in terms of its running time, even the leakage functions that it's computing aren't bounded. They can run the leakage can be an exponential time function, double exponential time function, as long as it's of bounded length, as long as the total amount of leakage from each step is bounded.
right. The simulator queries his Oracle only on inputs that were computed by the adversary, or does he query more?
Yeah, so in fact, it's even stronger than what I'm saying here. In the real world, the leakage adversary is choosing inputs and then seeing leakage and outputs. And all the simulator needs, it doesn't need arbitrary black box access to the functionality. It just needs the inputs and the outputs that the real world adversary asked for.
So it really preserves the security of the.
Right.
And so is the simulator is efficient or not?
The simulator is efficient.
Assuming
As
the
efficient as
adversary is efficient. I mean,
it preserves the efficiency of the adversary.
I see.
The adversary and the leakage functions it shows.
So it's like black box access to the adversary, it's efficient.
Right. So that's the main theorem. Before I tell you a little bit more about how we get it, I do want to mention the related work that's been done specifically on this question of general compilers. Okay, general compilers for transforming any computation to be leakage resilient. So the first work along these lines that I'm aware of is a work of Ishai, Sahai, and Wagner that showed how to compile circuits to resist what they called wire probe leakage, where the adversary can see the values of some limited amount of wires inside the circuit. Okay, so very specific kind of leakage, and they showed how to do this unconditionally with no hardware. They showed it without assuming something like only computation leaks information, but you can get a better leak if you want to assume only computation leaks information. You can get a better leakage bound. You can take the result; it's easily transferred, and you get a better leakage bound. And this was improved, or later work of Itai gave an improved result in the RAM model. So it's a slightly, ISW worked in a circuit model, Itai worked in a RAM model. He gave a similar flavor of result, but with better leakage rates. So the amount of leakage he could handle was better. So these are works that are known, these are basically the works that are known that don't use secure hardware. There has been a fair amount of work on compilers that use secure hardware. What this means is that instead of just having a leaky CPU, there are areas inside the CPU, there are areas inside the computation that the adversary can't see at all. Okay, so for example, you can do things like generate a ciphertext where the adversary doesn't see the randomness, where the randomness that's being used for the generation. So using secure hardware, using perfectly opaque components that the adversary can't see any leakage in, there's been a line of work. Faust et al. Showed how to resist AC0 leakage without assuming anything like only computation leaks information, without assuming any sort of cryptographic or computational assumptions, but using secure hardware. In work with Shafi and also work of Juma and Vallis, it was shown how to get a general compiler for OC leakage, for the local leakage that I'm talking about today, both under the DDH assumption and using fully homomorphic encryption. An independent work to ours of Zimbowski and Faust shows how to handle only computation leakage without any assumptions. Okay, so without the DDH and the fully homomorphic encryption that were used in prior works, it still uses secure hardware. Okay, so it still makes use of secure hardware. So that's essentially what was known for general compilers previously. The new result differs in that it doesn't use any secure hardware and it doesn't make any assumptions, and it handles a richer class of leakage functions, namely this OC leakage. There has been follow-up work that shows how to handle AC0 leakage, the same as this work of Faust et al., but without using hardware, at the price of introducing a computational assumption.
So this is orthogonal, right? You're saying it's orthogonal to this work because...
So it actually uses the tools introduced in this work, but it's incomparable because the leakage class is different.
You can do the best. You can combine them so you can handle both OC leakage and AC0 leakage.
I haven't thought about that. What if you compile the OC stuff using the AC0 compiler? You resist both.
You want to get a construction that resists both AC0 and OCL? But
Yes.
I see.
Maybe. I haven't thought about it, so I don't want to risk an answer online. One way won't work. AC0 and then OC. Using the AC0 and then the OC won't work. I don't know. So I'm not sure. You can get both.
So the last result is not for OC, right? I mean, it's for general. So leakage that can look at the entire state.
Yeah.
Doesn't mean anything for obfuscation. Going back, right? So you're saying, obfuscation means that you cannot do. You can do this. So there cannot be.
I think it might. Yeah, you could think of it probably. You might be able to think about it as an obfuscation versus AC0 adversaries.
You're saying there's no impossibility in that.
Right. That's a good point.
It's hard for me to see it online. Maybe Amit knows, but maybe in our impossibility for a result for obfuscation, it's implicitly assumed that translating it to this setting, the leakage function was more complicated than the actual circuit.
I think it was roughly of the same complexity as the original circuit, but the original circuit wasn't an AC0 circuit.
Right, so, but whatever the circuit was, we had something with a twist on it. So
Right.
in some sense, you could in principle have, as long as the leakage is simpler than the...
Right. The problem is that we don't have lower bounds for above AC0, so.
But yeah, maybe roughly speaking, we needed PRFs. So if you have a class that has PRFs, then somehow it's...
Right, maybe. Okay. So let me tell you a little bit about, maybe a little more than a little bit, about our compiler and how it works. And basically I'm going to separate it into three components. The first component, an initial tool that we'll use throughout, is what we call an encryption scheme that's resilient to only computation leakage. So it's a very simple encryption scheme that will be the basic building block for everything that comes after it. And then using this encryption scheme, we operate in two steps, or I'll present it in two steps. The first is how to run a single execution in a leakage resilient matter. And basically what I'll show is given secure encryptions of the secret Y, using this basic encryption scheme, how you can sort of safely compute the output of the circuit, even under leakage, just once. So you're given secure encryptions of Y, and even under leakage, you can just once compute the output of the circuit. And then once we have that, We'll show how to go to multiple executions. And basically the idea here will be orthogonal or sort of completely separate. What we'll show is how to repeatedly generate secure encryptions of Y in each execution. So in each execution, what we'll do is we'll generate a secure encryption of Y, and then we'll run the single execution sort of protocol, or the single execution computation. But it all starts with the encryption scheme, so let's start with that. So it's very simple, as you'll see, and we call this a leakage resilient one-time pad. It's a private key crypto system. And all it does is the key is basically a vector, a kappa bit vector vector 0, 1 to the kappa that's chosen uniformly random. And then to encrypt a bit B, what you do is you just choose a uniformly random vector whose inner product with the key equals B. Okay, so to encrypt the bit 0, you just choose a uniformly random vector that's orthogonal to the key. And to encrypt the bit 1, you just choose a uniformly random vector whose inner product with key equals 1. That's encryption, and decryption, as you might guess, is simple. Given a ciphertext in the key, you just compute their inner product. That's the bit that was encrypted. Okay. So that's all we'll use. That's essentially that's the information theoretic crypto that will be the building block on which the construction will be based. So it's a simple scheme, but it's going to have several useful properties for us. The first thing is I told you this is an encryption scheme that resists OC leakage, or resists only computation leakage. What I meant by that is that if there's separate leakage, if there's leakage that operates separately on the key and on the ciphertext, the bit that's encrypted remains hidden. Okay? So in particular, as long as we never compute on the key in our construction, as long as we never compute on the key and the ciphertext in the same subcomputation, in the same step, the bits that's encrypted should remain hidden. And why is this the case? Well, if the leakage operates separately on the key and the ciphertext, then one can show that even given the leakage, if you think of the key and the ciphertext given the leakage as random variables, then they're independent. Okay? Because the leakage never operated on them together, given the leakage, the key and the ciphertext remain independent. Moreover, since the leakage is bounded, given the leakage, the key and the ciphertext have a lot of entropy in them. Okay, if I only leaked one bit of information about the key, one bit of information about the ciphertext, then given this bit, the key and the ciphertext still have a lot of entropy in them. Now, we have here two sources that are independent and have high min entropy. What this means is that if we put them into a two-source extractor, or if we take their inner product, the inner product is statistically close to uniform. Okay? This follows from an older result of Shor and Goldreich. Particularly what they show, or what we can conclude from their result, is that given the leakage, the inner product of the key and the ciphertext looks completely uniform, statistically close to uniform. Okay, so the bit that's encrypted remains hidden. That's the first property we'll use. Another useful property is homomorphic addition. So if I take two ciphertexts, two vectors that are encrypted under the same key, and I add them, I do bitwise addition to the two vectors, I get a ciphertext that encrypts the bitwise addition, the bitwise XOR of the bits that they encrypted. So C1 plus C2 encrypts the bit B1 plus B2.
So, Guy, in this encryption scheme, all the operations are over Z2. Should we think of it as
over GF2, yeah. Everything is over GF2. So it's all bit operations, and addition is XOR. And you can also do, so this is homomorphic addition of two ciphertexts. You can also easily add a plain text to a ciphertext.
Without knowing the key? Without knowing the key?
Without knowing the key, I'm cheating here a little bit. But by an easy tweak on this scheme, if you add an extra bit to the beginning of the vector, then you can do this. And another property that I won't talk about so much, but is actually very important, is what we call key ciphertext refresh. And what this says is that we can take any key and ciphertext, and by operating on the key separately and the ciphertext separately, generate a new, say, key prime and ciphertext prime that are uniformly random under the condition that they maintain the underlying plaintext, that they encrypt the same bit. And that's also a property that we use and is important. But I won't talk about it today. So that's our encryption scheme. Those are the properties. And now how do we use it to do a single execution in a leakage resilient manner? So I'll think about the circuit C as being composed of NAND gates, following along the previous talks today, or at least Jens's talk. So we have a circuit of NAND gates. For now, think about just having one global key for the execution. Okay? And every wire K, so now that once the input is fixed, every wire K has a bit value B sub K. Okay? And the sort of guiding principle for running the computation will be that we never ever store or compute this bit, the bit value of any wire except the output wire, in the clear. Okay? If we ever compute or store the bit value of a wire, that can leak out to the adversary through the leakage. It's non-black box information and security is lost. So we never do that. Instead, we'll only work on these bits in encrypted form. So for every wire K, we'll have a ciphertext C sub K that is an encryption of the bit value of that wire. And we'll only work with these encryptions. The idea for running a single execution is to assume that we have the ciphertext for the input wires, okay, for the Y wires. So we have the bits of Y in encrypted form. What we show is a way to compute the ciphertext for all the intermediate wires, for all the intermediate NAND gates, homomorphically while only operating separately on the key and on the ciphertext. Okay, so we compute all the intermediate ciphertexts homomorphically, working separately on key and ciphertext. Since the scheme resists independent leakage or separate leakage from the key and the ciphertext, this doesn't expose any information about the actual values on the wire. So the main challenge, okay, given that we assume that we have, or we're given the ciphertext for the input wires, the main challenge is computing the ciphertext for the intermediate wires. The way this is done is through what we call a safe homomorphic NAND procedure, where what we have is we have as input, we have a ciphertext for wire I, we have a ciphertext encrypting the value of wire I, we have a ciphertext for wire J. What we want is to compute a ciphertext for the output wire, for wire K, that encrypts the NAND of BI and B sub J. Okay, so for this we have a safe NAND procedure. It gets as input the key and the input ciphertext. It should output the output ciphertext. And the way this procedure works is very simple. First, it generates a ciphertext, just a dummy ciphertext, encrypting a random bit. Okay? I won't tell you exactly how this is done, but we can do this, and we just generate an encryption of a random bit, where the adversary doesn't know what the random bit inside the encryption is. We never access the key while we're doing this, so the bit inside the ciphertext remains hidden. Okay? So we have some dummy encryption of a random bit that may not seem like a lot, but then what we show is that given that, we can actually safely compute the NAND that we want masked with this random bit, okay, in the clear. Yeah, you know?
Right, the encryption of a random bit is just a random string of linked copper, right?
Right. In fact, we need to work a little bit harder than that. But yes, sorry, let me just say I'm cheating, but the answer is yes. If you just choose a random vector, then it encrypts, its inner product with the key will be a random bit. You don't need to touch the key. It's hidden from the adversary.
Right, but I should think of this encryption as an encryption with respect to the key that's in the input.
Yeah, yeah. Everything, I'm also cheating in this, but everything is being done under one global key, the entire computation, for now.
For now.
Yeah, and for the talk today. And if you want to see how we do it with different keys or how we avoid accumulating leakage on the key, then you can go to the paper, but I won't talk about it today. Okay, so what we show now is the next step is to actually compute the NAND, the plain text of the NAND masked with this random bit. Okay? So this is some intermediate value. Notice that even if this is exposed to the adversary, it doesn't mean anything. Since this is a random bit, what we get is also random. Okay, so this doesn't expose any information about BI and B sub J. And then once we have this, we just toggle the dummy ciphertext that we had, this CK prime. We just add to it an encryption of this bit, or we just add this bit, and this gives us an encryption of really what we wanted, which is the NAND of B sub I and B sub J. Okay. So this is how the safe NAND procedure operates. The difficult part, or the part that I'll tell you a little bit more about, is how do we actually do this? How do we actually compute the plain text the plaintext masked value, the NAND masked with this RK in a leakage resilient matter. Okay. So again, what we have is we have these input ciphertexts, we have a dummy ciphertext CK prime that encrypts some random bit RK, and now we want to safely compute the plaintext, the masked plaintext. And the way we'll do this, or an initial idea for doing this, which follows along earlier, or follows along the lines of what was done in earlier work by Sanders, Jung, and Young, is to homomorphically compute a four tuple of encryptions. Okay? We have homomorphic addition, and we can use that to compute this four tuple, a four tuple encrypting these 4 bits. Okay? Just using homomorphic addition. And if you're very quick, while the slide is still up, you can verify that if the value we're after, if this AK is 0, then this 4 tuple will have 3 encryptions of zeros and 1 encryption of 1. And if the value we're after is 1, the 4 tuple will have 3 encryptions of 1 and a single encryption of 0. Okay. So once we compute this 4 tuple, the initial idea is, well, why don't we just take these 4 ciphertexts and decrypt them? Okay, and we'll see if we have 3 zeros and a single 1 or 3 1s and a single 0. So any objections to this idea? So the problem is, well, let's look at this 4 tuple, right? Let's say we decrypt the 4 ciphertexts in the 4 tuple. What we get in the first location is RK, and in the second location we see BI plus RK. So in particular, we can XOR them and retrieve the value of BI. Right? This exposes the wire value on the input wire I. That's non-black box information, and that's insecure. Okay, we have to protect all of the wire values. Oh, sorry, yeah. So that's no good, and the problem is that while we want to retrieve the number of zeros and ones, we don't want to leak any additional information beyond the number of zeros and the number of ones. In particular, the order or the locations of zeros and ones might leak non-black box information. So what we're concerned about is the order of what's leaked. Naturally, what we'll do is we'll try to randomly permute this 4 tuple of encryptions. Okay, once we have a random permutation, there's no more information about the order, and we can just decrypt and see how many zeros and how many ones we have. Okay, so why can't we just activate a random permutation? This is Sanders, Jung, and Young activated a random permutation. Why can't we do that? The idea is we can't do that because the permutation we activate will also leak. Okay, so if we activate a permutation, now the adversary knows information about the permutation. Again, when we decrypt, the adversary can reconstruct information about where the zeros and the ones were. Okay, so what we need is a leakage resilient permutation, a way of permuting even in the presence of leakage.
So Guy, sorry, just to check. So here you're not worried if the attacker learns this value AK. You just want to make sure he doesn't know the partial results. Right? So
Right. AK, well, the adversary will learn AK because we're computing it. Anything we compute leaks to the adversary.
Well, you want to compute encryption of AK, but you're saying you.
No, I want to compute AK itself.
Oh, you want
the
to
plain
compute
text. That's why I'm decrypting.
Nice. And you're saying, I mean, and this should be easy to check. If you had a magic permutation, then if I give you those 4 values in random order, that doesn't leak anything except for AK.
Right. So I'll briefly tell you about this leakage resilient permutation, how we can get a uniformly random permutation even in the presence of leakage. And the idea is that we'll have the following procedure. We have a 4 tuple of ciphertexts, okay, ciphertexts and keys. And what we'll do is we'll duplicate this 4 tuple many, many times. So now we'll have many copies of this 4 tuple, say kappa of them or k of them. We'll refresh each copy independent. So now they're just copies. We haven't done anything. We just have many copies of the same thing. But now we run the refresh on each copy independently. And now we have many copies. We have many tuples that encrypt the same bits. But other than the fact that they encrypt the same bits, they're statistically independent. Okay? Now, what we'll do is we'll permute each of these copies independently. And the idea is that if we do this, the adversary can learn a little bit about, say, the first tuple. He can learn the first permutation. The permutation we activate on the first tuple can leak. And maybe the permutation we activate on the second tuple can leak. But because the leakage is of bounded length, the adversary can't learn too much on about too many of these permutations.
So the leakage is smaller than the amount
Yes.
of leakage smaller than the amount.
Yes. Yes, so the computation here is of size kappa squared, and the leakage is of size less than kappa. Okay, and the fact that you can show is that even given the leakage and the inputs and the outputs, most permutations look fairly random. Most permutations have a lot of entropy in them. And now what we'll do is we'll just choose one of the copies at random. Okay, so with high probability, what we have is a copy that was permuted using a permutation that the adversary doesn't know much about. And then we'll repeat this many times. And we can show that if there's a lot of if most of the permutations that we activated, in most of the iterations, the permutations had a lot of entropy in them, then the composed permutation will be statistically close to uniform.
Since you repeat many times, you mean like sequentially? Sorry.
Yeah, sequentially. So
So
we're
each time,
compo-
so
yeah.
you duplicate, you pick like one copy,
Mhm.
then again you just take this one copy, duplicate, and so on.
Yeah, yeah.
But what
And-
if you fail the very first time?
So that's fine. So what you need is that you've activated a sequence, you've composed a sequence of permutations. Most of them have a lot of entropy. And so even if the first one has no entropy and the fifth one has no entropy, the intermediate ones will give sufficient entropy for the composition to look uniformly random.
But you still need entropy of, you still need that after, the first step, the attacker doesn't learn, like, let's say, the first two values, the values of the first two planes.
No. So we're not decrypting anything along the way. So this is all done while never loading keys and ciphertext into memory at once. Yeah. Okay. So this gives us a uniformly random permutation, and using this we can do NANDs and we can do a one-time computation that's secure against leakage. Okay. So what we did, notice here, is that what we assumed is that we had the ciphertext for the input wires. The ciphertext for Y were generated beforehand. We had them and we could start this whole process. But even if we had encryptions of Y to begin with, if we ran multiple executions, over time the leakage on these encryptions of Y would accumulate and they would become insecure. We can only allow a bounded amount of leakage on each ciphertext. So we can't do an unbounded number of executions. Eventually the leakage would accumulate and we would lose security. Bits of Y would be exposed. This was a problem that appeared in all the previous works that I told you about. And generally, sort of very broadly speaking, it was solved using secure hardware. So the secure hardware would generate fresh encryptions every time, and the assumption was that the adversary can't see what's going on inside the secure hardware. And so security is maintained even for multiple executions. Okay? And this is really where we're getting rid of the secure hardware. What we want to do is to repeatedly produce fresh, secure encryptions of the bits of Y, even under leakage, without using any secure hardware.
Can I ask you a question? Sorry. So I'm going back a second. So you had the four ciphertext. You generated a truly random, secret permutation because you did it many times. So
Right.
it didn't leak and it's good. So now what you managed to do is to take the four ciphertexts and really permute them in a good way.
Right.
But is it clear that even if they're permuted randomly, that they don't reveal any information? Because the key, maybe
So I glossed over one other detail that was lost along the way, is that we're activating this refresh procedure that every time takes the ciphertext and produces uniformly random ones, and we're doing it many times. So,
Okay, got it. Okay.
yeah. So it's not clear. But,
Okay.
Good. So what we want now is to repeatedly produce these encryptions of Y, and then once we have secure encryptions of Y, we can activate this one-time computation. So the one-time computation procedure with the permutations and compute the outputs many times. So the way we do this is using what we call a ciphertext bank, a new object or a new technique. And the way this ciphertext bank works is you initialize it. It's an object, you initialize it with a bit value 0 or 1, and then you can repeatedly use it to generate key ciphertext pairs that all encrypt the bit value B. Okay, so you can use the ciphertext bank to generate key 1, ciphertext 1, key 2, ciphertext 2, etc., etc. All of these will encrypt the initial bit value that the ciphertext bank was initialized to produce. Okay, so it either generates encryptions of zeros or encryptions of 1. In terms of security, what we can show is that actually it's indistinguishable from a simulated ciphertext bank. So we have a simulator, and the simulator can generate any encryptions of any bits that it wants. Okay? So whatever bits you want the simulator to generate, it generates keys and ciphertext encrypting those bits. So the first bit could be 0, then 1, then 1, then 0. It doesn't have to be the same thing. It's completely under the simulator's control. And leakage, OC leakage, from real and simulated executions is statistically close. Okay? So notice that there's an initialization step, which is very different. We'll talk about it in a minute, for the real ciphertext bank and the simulated one, and we assume there that there's no leakage. But after this initialization, you can repeatedly, in the simulator, you can repeatedly generate keys in ciphertext that encrypt any bits that you want, and no leakage adversary will be able to tell the difference. So how does it work? Well, for the real ciphertext bank, initially what we do is we just choose M. Think of M as something about the same order of magnitude as kappa, as a security parameter. So we generate M ciphertexts, C1 up to Cm, all encrypting the same bit, B. Okay, and there's a key, and they all encrypt. They're all encryptions of the same bit B under this key. To generate a new ciphertext, what you do is just take a random linear combination of these ciphertexts. Okay? Moreover, I'll ask for a random linear combination that has odd parity. So the way it looks is we think of these M ciphertexts as being the columns of a matrix. So initially we have this matrix that has columns C1 up to Cm. We multiply it by we take a random linear combination, which is the same as multiplying it by a random vector with odd parity, with an odd number of ones, and out comes a new ciphertext. And it's easy to verify that if all of these were encryptions of 0, if all of them were orthogonal to the key, then any linear combination will also be orthogonal to the key, so you'll get an encryption of 0. And if all of these were encryptions of 1, then because we're taking a linear combination with odd parity, what we'll get is an encryption of 1. Okay, so that's for functionality. That's the way we use the ciphertext bank to generate one new ciphertext. For simulated generation, instead of taking M ciphertexts all encrypting the same bit B, we'll take them to encrypt different and uniformly random bits. Okay, so the bits encrypted in the columns of the matrix are just uniformly random bits. There are M of them, so we think of them as a uniformly random vector. Okay, so they encrypt uniformly random bits. And now to generate a new ciphertext on input B, which can be either 0 or 1, I have no idea what it's going to be. I just take a random linear combination, or the simulator just takes a random linear combination with odd parity, such that the inner product of X, such that the bit encrypted by the ciphertext, resulting in taking this linear combination, will be B. This is equivalent to saying that the inner product of the linear combination R with the vector of encrypted bits X is equal to B. Just linear algebra.
So this is all under the same key, right?
Hmm?
This is all under the same
All
key.
under the same key.
But that's a simplification, right? Because you're going to generate ciphertext.
So just for one generation. For a single generation, it's fine to have the same key. And when I talk about multiple generations, I won't discuss it, but we'll need to refresh the key between from one generation to the next generation.
Here the simulator knows B, right?
Yeah. So the simulator is given, it's given some arbitrary bit B, and it needs to generate a ciphertext encrypting this bit B.
But his hands are tied, well, not completely, but it's tied because at initialization he is forced to encrypt X.
Right. But he chooses X. The simulator also chooses X.
Right.
But X is a uniformly random vector, so there will be many linear combinations leading to 0, many linear combinations leading to 1. And now the question is whether this is secure. Okay, so the point or the reason why it might be secure is if all you see is leakage from this R, from the linear combination, and you don't know anything about X, it's not going to, or you only have a limited amount of leakage on X, you have no idea what the inner product is of R and X. You can't distinguish whether this R was chosen in a biased way to guarantee that the output would be B, or whether it was chosen to be uniformly random with odd parity.
Sorry, but there is, in the simulator, simulates leakage. There is no leakage in the simulated world, right? He just does something.
So the simulator basically simulates an execution, and then the leakage is activated on that execution.
So in particular, he has to pretend to do whatever the attacker does. Not the attacker, the real guy.
Yeah. So he's basically choosing randomness
Right.
for the real guy.
Right, I see. So essentially, he generates a bunch of these vectors R, gets this matrix, and I see.
Mhm.
And we just live on this matrix, right?
Yeah. So he's basically setting up an execution, and then later we'll activate the leakage, and we'll argue that they're indistinguishable. So the question is whether this is secure, and the answer is that it's not clear. It depends on how you compute matrix multiplication, right? So we have this matrix whose vectors are the ciphertext. We're computing on it, and the question is how we compute. So if we were to do naive matrix multiplication, it would be insecure. Why? Well, think about a real execution where the columns all encrypt 0. Okay, so the columns are all orthogonal to the key, so they're all in a linear subspace of dimension kappa minus 1. In the real execution, all the columns are in a linear subspace of dimension kappa minus 1. Whereas in the simulated, we just said that the columns are uniformly random. Okay, so with one bit of leakage, just computing whether the matrix C has rank kappa or kappa minus 1, you can distinguish the real and the simulated executions. Okay, so this, as I presented it, is not secured. Still, at least looking at this attack really required you to load a lot of the columns into memory so you could distinguish whether they were all in a linear subspace or not. If all you loaded was kappa over 2 columns, you wouldn't be able to distinguish whether they were in a linear subspace of small dimension or just uniformly random. And in fact, what we show, in fact, this is what we'll do. We'll never load all of the columns into memory at once. We'll divide the matrix multiplication into a constant number of substeps, where in each substep, we'll only load a small number of columns or a small number of linear combinations of columns into memory. Okay, matrix multiplication has this nice structure where you can actually separate it into substeps, where in each substep, you only load a small piece of the matrix into memory, where by piece I mean either a small subset of the columns or a small number of linear combinations of the columns. Okay, so we call this piecemeal matrix multiplication because it's really computing the multiplication just using the matrix piece by piece, never using the entire matrix at once. So if you use this piecemeal matrix multiplication, in fact, it can be shown that the multiplication is secure, that the construction is secure. So as long as all you do is you load some constant fraction of kappa linear combinations of columns into memory at any one time, what we can show is that the real execution, or access to the real matrix where all the columns are in a subspace of degree kappa minus 1, and the simulated execution where the columns are all uniformly random, look the same. As long as the leakage is only allowed to operate separately on each piece of the matrix.
So sorry, what do you mean by linear combination of columns? Why not columns itself?
So if you think about now, even compute just a linear combination of the matrix columns. Okay, so you take the first, I don't know, say the first kappa over 2 columns, and you compute whatever you want, the linear combination. And now what you want to do is to load that linear combination together with the next kappa over 2 columns. So you're not just loading, in the second step, you're not just loading columns into memory, you're also loading a linear combination of the previous columns. So to carry over information from before, you need to talk about linear combinations. But the same intuition holds for linear combinations, so you may as well think about it as just, for security, you may as well think about it as just loading columns into memory.
So in your assumption, I just want to so you have a freedom how to partition your computation into local substeps, and they have to be, I'm just trying to make sure, so you choose the size of those things somehow?
Yeah, so we're choosing the size of it. I think the way I like to think about it is in this leaky CPU model, where I have a CPU, I have a set of atomic instructions. One of the atomic instructions is matrix multiplication for these kinds of matrices. But yeah, in general, all the works in this OC model have to face this sort of question about who decides what the breakup into subcomputations is. Good. So that's how we do. A single generation. In fact, what we'll want to do, we can't just reuse the same. This goes back to Vinod's question. We can't reuse the same matrix over and over again because eventually leakage will accumulate. So in fact, what we do is every time we want to generate one ciphertext, we generate m plus 1 ciphertext. So we take the old bank with m ciphertext. We take m plus 1 random linear combinations, all of odd parity, and that gives us m plus 1 new ciphertext. The first m we'll use for the next generation, and the n plus 1 we use for whatever we need it for. That's the new ciphertext that we generate. Okay. And maybe I won't tell you too much about the security, And I'll just sum up here. So what I showed you is how to compile any computation into one that resists these kinds of local leakage attacks, or works in the leaky CPU model. There wasn't the need to use any secure hardware, and we didn't use any computational assumptions. What I wanted to end by is just talking about it at a slightly higher level. You can think about this as a method for dividing any computation that's going to be performed many times into pieces, such that leakage on individual pieces, each piece on its own, exposes nothing about the global structure of the computation. So it's a way of setting up computation such that local views leak nothing about what's happening globally. And in fact, this approach, or this way of dividing computations, has found subsequent applications. One to obfuscation with leaky hardware, where we basically think of these different pieces as secure hardware devices, each of which can leak on, and the adversary controls the communication channels between the devices. That's an extra challenge. And also, it's found applications to taking general multi-party computation protocols and making them leakage resilient. This is in work of Boyle, Goldwasser, Jane, and Kalai, where you just think of these different pieces, the different local views of the computation, as what different parties in the protocol see. And now you have additional challenges because parties can be completely corrupted, and also the adversary can view the communication between the parties in its entirety.
The model of security is different, right? I mean, today it's like whatever you leak in the real model, you leak in the ideal model or something like that.
No.
It is.
No. I don't know if Yael wants to say something more than no. Okay, and that's all I wanted to say. Thank you.
Questions? Questions for Guy? So one could think of this perhaps stronger model where you have two CPUs, right? And you can leak from this CPU or the other, but you cannot leak, you know. It's not the OC model, but it's sort of the two CPU model, right? So that's
Is it weaker or stronger?
I'm not sure. Right?
Uh-huh.
Yeah.
But the question is whether you can also leak on what's in memory.
You
That's
can
not
leak
in
on both the
CPUs.
CPUs, but independently, right?
Mhm. So I think that's a weaker model, because here you can leak on all the computation that's happening together.
No, it's a stronger model.
So the model that I'm speaking about, sort of your OC in space and your OC in time.
Oh, he's saying two processors. He's saying like the dual level mode in Velis.
Yeah, that's about.
Just two processors
That's
rather than many
yeah.
processors.
Right.
If you can get it.
I mean, I think so. I still think that.
There's no assumptions in their hardware.
You don't have granularity. So
Oh,
it's like 2 gigabytes of 1 gigabyte here, 1 gigabyte here.
Oh, I see. So there's no memory aside from what's happening in the two processors. So I'm wondering if you could transform that into this model by always running them, instead of running them together, just running one CPU and then shipping everything back off into memory and then getting back the information for the second CPU and running that, and sort of alternating.
Take this offline.
Okay.
Right. Any other questions? Good. Let's thank Guy for a wonderful talk.